Hello class, welcome to subtopic 1.6, which is about the concept of demonstration, and in particular we will be using the direct method to demonstrate statements like this. You're going to notice that most of the statements or most of the theorems that I'm going to be telling you to demonstrate are quite simple, and we're going to use this method, which is called the direct method, from left hand side, lado de el lado izquierdo de una ecuación, to the right hand side, al lado derecho. You're going to understand what this means in a moment. Okay, let's begin. I'm going to show you 3 examples of how this is carried out. It's extremely simple, you will notice. And so here we go. So this first statement, this is a theorem, I told you, right? When you write a statement and you're gonna prove it, you're gonna provide a demonstration, then that's called a theorem. I'm saying that this is equal to this, and therefore I need to demonstrate such a claim. So you usually write the theorem, there you go, and then you write demonstration, and then you carry out the demonstration. Why is this method called the direct method, or the left hand side to right hand side method? Because the goal is to choose one of the sides, either the left hand side or the right hand side, and then arriving at the other side. For example, in this case, what I'm going to do is this. I'm going to choose this side, this expression, and I'm going to demonstrate that this expression is equal to this other expression. How do I start? Most of the times I start with the law of identity, which is the following. The law of identity tells you that something is equal to itself. This is called the law of identity, and it dates back to Aristotle. This is a very simple law or axiom. It's also basically it's an axiom, okay? The axiom of identity. Something is equal to itself. So I'm going to start this way. Then, remember how you pronounce this little arrow? Then I'm going to do this. Then x plus y squared equals, and on the right hand side, in this case, I'm going to actually perform the multiplication of x plus y times itself, because basically that's what I'm doing, right? I'm raising x plus y to the square, and that means the following: x plus y times x plus y. You see, this was my second step in my chain of reasonings. Then x plus y squared equals, and then on the right hand side we carry out the multiplication of x plus y times x plus y. So we go x times x, x squared, x times y, xy, y times x, xy, and y times y, which is y squared. You see, we have another step in the demonstration. And then x plus y squared is going to be equal to, we collect these two like terms, and we get x squared plus 2xy plus y squared. And if you notice, guys, we have already demonstrated beginning. This is my first step in the demonstration. My first step is assuming this to be true. You see, because it is true. It's such an obvious thing. It's an axiom. Something is equal to itself. And then I perform little steps, little by little, until I arrive at precisely the thing that I wanted to demonstrate, which is the fact that x plus y squared is equal to all of this, just like you see in here. You see? So all of this is the demonstration of this theorem. It's a very simple theorem. You already knew it, right? And let me show you another thing that we're going to be using a lot in demonstrations. I'm going to write this little square. Let me tell you what this is. This is known as the Halmos Halmos tombstone. La lápida de Halmos. Halmos was a mathematician in the 20s, I believe, from Hungary, I believe. I'm not 100% sure. And this guy invented this symbol in order to symbolize the end of a demonstration. So basically, this is the end of a demonstration. It's a little square, black. It's a black square, but I mean, of course, I need to use white in this case because. And that's it. That's how it works, guys. This is the complete demonstration of this theorem. Next example, B. Theorem. I want to demonstrate that x squared minus y squared over x plus y is equal to x minus y when x is different than y. I'm gonna explain to you what this means in a moment. For the moment, if you want, just ignore this. Okay, so this is what I want to demonstrate. I want to demonstrate that this fraction is equal to this expression. So let's start. Demonstration. Okay, so I'm gonna decide to bring this side so that it looks like this side. So I'm gonna begin doing this. I'm gonna write the left hand side, and I'm gonna say that it's equal to itself because that's obviously a truth. It's equal to itself, right? This is my first step in the demonstration, and as I told you, this is called the law of identity or the axiom of identity. Anything is equal to itself. Then the second step is this. If you notice, the left hand side is always kept the same. So you may as well, if you want, you may as well ignore that step or skip that step. Basically, in the left hand side, we're gonna just keep the same thing that we had above. So this, which is gonna be here, is gonna be equal to the following. On the right hand side, I'm gonna factorize this difference of squares. And if you remember from the previous semester, the factorization is this, a product of conjugated binomials. Okay, so basically in this line, I'm saying that this is equal to this, and this should be written here, but you can skip it because it's always going to be the same, just like in here. Can you see? It's always the same, so you can skip that part if you want. Okay, now what next can I do on the right hand side? Look at this. We have this factor times this factor divided by this factor. So we have equal factors up and below, which is this and this, and therefore we can cancel them, right? We can do this, x minus y, and then I can just cancel both factors. I can cancel this and this, and then my next step is saying that this fraction, which is written here, but I'm just ignoring it for the moment, is equal to, since I already canceled this factor and this factor, all I'm going to be left with is x minus y. And at the end, if it's preferable to go back to the full expression, which is that this should be written here. So let me write it down. X squared minus y squared over x plus y equals x minus y. And this is the full demonstration. So we symbolize the end of the demonstration by the Halmos tombstone, which basically means end of proof. End of proof. There you go. And this completes the whole demonstration. Remember, guys, in here, technically speaking, in this step, in this part, and in this part of the equation, you should write this. but it takes too long, and I know it's kind of cumbersome. So if you want to skip it, that's fine. Just go back to it at the end of the demonstration. Now, why did I say this at the beginning? That x should be different than y. Why is this equal to this as long as x is different than y? Because in the case of x being equals to y, no, I'm sorry guys, I made a mistake, a small mistake in here. Let me correct that. As long as x is different than minus y. Is that the right one? Yes. Well, let me put it another way. I hope I don't confuse you guys. Let me put it in a simpler way. As long as x plus y is different than 0. This is the best way to put it. We need to add this caveat or this restriction. This is equal to this as long as x plus y is different than 0. Because remember, x plus y cannot be equal than 0. Okay? So we need to discard this possibility. As long as x plus y is different than 0. But if you, I know this is too technical. If you want to just ignore it for the moment, that's fine. Just try to understand all I said in these steps. And final example. I want to demonstrate the following theorem, that 1 over m plus 1 plus 1 over m squared plus m equals 1 over m. So same idea. I want to demonstrate that all of this is equal to this, and my approach will be to actually manipulate all of this expression so that it ends up looking like this. And I need to do some algebraical manipulations, some additions, some stuff, okay? Remember, there is no way, guys, there is no way in which you can know what you need to do in advance. There is not a recipe for these demonstrations. You have to be creative. So let's start. I'm gonna first write the law of identity with this, all of this expression, this addition, and I'm gonna say that all of this is equal to itself. There you go. Law of identity. Something is equal to itself. Very simple to understand. Then all of this, which should be written right here, but I'm gonna skip, is equal to this, and I'm gonna start manipulating algebraically, algebraically manipulating this expression, this addition, so that I can somehow bring it to look like this. So it's an addition, and what I can do is this. I'm gonna use the method for adding fractions, right? Which is, remember, it's this number times this number, and it goes in here, and then this number times this number, and it goes in here. This times this goes here. I'm gonna repeat that. This times this goes here. This times this goes here, and then this times this in here. Okay, then this thing, which should be written here, is going to be equal to the following. I'm going to carry out the sum of this. I'm going to get m squared plus 2m plus 1, and I'm going to carry out the multiplication of this, which is going to give me m times m to the q, m to the square. You're going to get m to the 3 plus m squared when you multiply this times this, and then plus m squared again, and then plus m. Then this expression, which is written here, is equal to, I'm just gonna put together these two like terms, m to the cube plus 2m squared plus m. And then what I can see in here, guys, is that I can factorize. Can you see this expression? All of this expression has three terms can be factorized because we have a common factor of m. So I'm gonna try to factorize, and I'm gonna see if something happens. Remember, you don't know in advance that this is in fact what you have to do. You just have to try stuff. So we're gonna get that this is equal to the following: m squared plus 2m plus 1 over m, which is my common factor, that multiplies m squared plus 2m plus 1. Try to make sure this is equal to this, right? And then what I can observe is that once again I have common factors, equal factors up and below. If you notice, this factor is the same as this factor, and they can be cancelled. So we're gonna have the following. I'm gonna do the cancellation in this step. I just write it down, cancel it, and then I finally arrive at what I had in the beginning, right? Once I cancel this and this, all I get is 1 over m. The m is in the denominator, so don't make a mistake. And now that you have actually proven that, remember, what is this? What do I mean by these 3 points? I mean this expression, guys. This expression is kept the same throughout the demonstration. I just skip it. I just don't write it down for simplicity's sake. But now that you have arrived at the final demonstration, the final conclusion, then go back to the original expression, which is this. Then 1 over m plus 1 plus 1 over m squared plus m equals 1 over m, which is what I wanted to demonstrate at the beginning. This is the conclusion that I'm arriving at. So end of the proof. There you go. Okay, remember, technically speaking, each of these 3 points should stand for this. So you actually have to write this down, but it's way too heavy on the hand. So if you want to ignore that thing, it's okay. And actually, you can leave just an empty space. People also do this, like they leave empty spaces like this, and we assume that what is in here is what is on top. Some other people do this, like this symbol, but I don't really suggest this. So just leave a space or those 3 points, or if you want to write it down. It's okay, no problem. So this is how it works, guys. You basically are in this type of proofs from left hand side to right hand side, or vice versa, okay, because it doesn't have to be from the left hand side to the right hand side. What if, for example, this theorem was written in this way? Instead of this, what if it was written like this? 1 over m equals 1 over m plus 1 plus 1 over m squared plus m. You can also bring this to look like this. So it can also go from right hand side to left hand side. It doesn't have to be strictly in this direction. Okay, so basically that's how it works. You're gonna manipulate algebraically one of the expressions and make it look like the other one. And that's how it works. It's a very simple method of proof, of demonstration. I'm gonna be helping you out in the rest of them if you have questions, because I'm gonna give you several examples of this. And remember, there is no way you can know what steps you need to perform. You need to try something. And hope for the best. And if something is not working, try something else. And if that something else is not working, try something else, etc., etc., until you finally arrive at the conclusion that you wanted to demonstrate in the first place. So there you go, guys. Thanks so much.